Okay, so good morning and thank you for joining us to the Elsevier Distinguished Lecture Award in a lecture in mechanics. I would love to introduce myself. My name is Lily Kidder, and I am the executive publisher for Mechanics Research Communications. I also would love to introduce the host of today's lecture, Professor Tony Rosato from the New Jersey Institute of Technology. He is the editor-in-chief of Mechanics Research Communications and has been instrumental in developing the Elsevier Distinguished Lecture Award in Mechanics. Tony, I will turn it over to you to introduce our distinguished guests today.
Thank you. I appreciate it. Thank you very much, Lily. So welcome again to the 7th. We're in the 17th lecture, distinguished lecture. So this has been going on for 17 years now, and thanks to the support from Elsevier, which has been really wonderful. The first lecture began on April 14th, 2008, was given by the late Professor Jan Achenbach. I'm delighted to introduce Dr. Félix Darve, who will speak to us today on granular material as a bifurcating complex system. Dr. Darve is Emeritus Professor at Grenoble INP, Grenoble Alpes University at CNRS in France. He serves as the editor of the International Journal for Numerical and Analytical Methods in Geomechanics. He is the former director of the Grenoble National School of Hydraulics and Mechanics, the CNRS National Laboratory, and the European Network of Laboratories Alert Geomaterials. He has edited and co-edited 16 books and is the author or co-author of more than 300 peer-reviewed papers. His main research topic is computational granular mechanics with applications to natural hazards. And I would also like to say that this is actually the very first time that we have a speaker from Europe. All the previous lectures have been from the United States, so I'm extremely delighted that Professor Darve will speak to us today from France.
And just one thing, we won't be charging any tariffs for the lecture.
Yes, no tariffs, so don't worry. So the protocol, just a word on protocol, during the lecture, no questions will be taken. However, through the Q&A box at the top, participants can put questions in that box. And after the lecture, depending on time, Professor Darve can answer your questions. And we do that to ensure anonymity. Participants' mics will be disabled during the lecture. So without further ado, I turn over the podium to Professor Darve. Thank you. Yeah.
Thank you for Elsevier for organizing this series of distinguished lectures. And thank you also, of course, to Tony for this nice introduction. So today I will talk about granular material, and indeed granular material are very specific media. If we compare granular media to solid state, liquid state, or gas state, and probably the main differences, the main specificities of granular materials are due to the fact, first, this is a complex system, and two, their plastic behavior is non-associated, leading to a lot of bifurcation. And this bifurcation in practice are leading to many catastrophic events like earthquakes, landslides, rock falls, snow avalanches, and so on. So I will consider successively, first, as an introduction, this question of complex system, then go to granular plasticity and show you the specific features of plasticity applied to granular materials. In a second part, we will apply bifurcation criterion to some elastoplastic constitutive relation, then validate these results, the existence of a bifurcation domain, the existence of cone of unstable direction by direct numerical simulation, discrete element method, and finally give you an example, a practical example of a slope failure induced by bifurcation. So first, why granular material is a complex system, and absolutely to begin, what is the definition of a complex system? A complex system is constituted by a large number of entities which are exchanges information through some interaction laws. 2 points are important in this definition. First, we need a large number of grains. And second, there is question of information in its broad sense as proposed by Shannon, for example. So immediately we see that 3 scales have to be distinguished in a granular complex system: the scale of the grain, the microscale, the scale of some structure constituted by 10 or 20 grains, the mesoscale, and eventually the global scale, the macroscale. So at the mesoscale, we have some mesostructures typical of granular material, force chains and grain cycles, force chains which are constituted by grains more or less aligned, transmitting, roughly speaking, transmitting forces, stresses, and grain cycle composed by closed loops of grains, essentially responsible for the strains, for the deformation. And these mesostructures are continuously been selected. Only the strongest ones are surviving, and through this selection, they are adapting continuously. So, because of this continuous adaptation, collective macro behavior is rising by self-organization. And finally, because of this self-organization, some macro properties are emerging. The important point here are the process of selection, adaptation, self-organization, and emergence. And of course, a sand pile, roughly speaking, has extremely different properties. This is obvious from a sand grain. So granular material is a paradigmatic complex system which is athermal. Its behavior is fully independent of the thermodynamic temperature. This complex system is also atemporal because the physical time has not any influence. This is a non-viscous material. So it is independent, its behavior is independent to the loading rate. And finally, this complex system is leading to bifurcation, induces different instabilities, and finally failures. So, first part, after this introduction, few words about granular plasticity. Here you have a general presentation of the classical view of plasticity. Plastic materials are rate-independent materials. It means that the incremental stress is a function of the incremental strain. Because of the rate independency condition, non-viscosity, the tensorial function F is homogeneous of degree 1. We can apply Euler's identity and demonstrate the existence of an elastoplastic tensor linking d sigma to d epsilon. And because d sigma and d epsilon are symmetrical matrices, we can replace these matrices by vectors with 6 components. And in these new spaces, we have now a matrix M linking the vector d sigma to the vector d epsilon. What means perfect plasticity? What means failure? It means the possibility to have some strain, some finite strain for vanishing stresses. So, if in the constitutive relation we want to have non-vanishing strains for vanishing stresses, necessarily the matrix M must be singular, so its determinant must vanish. This is what is called the plastic limit condition from a mathematical point of view. And in perfect plasticity, we have this condition, M d epsilon equal to 0, which is called in the classic theory of plasticity, the plastic flow rule, giving only the direction of d epsilon because the determinant of M is equal to 0. But now we will see that according to experiments, the failure, the plasticity of granular material cannot be described in this classical plastic framework. Here you have experimental results corresponding to isochoric triaxial compression on a dense sand specimen. In soil mechanics, this kind of tests are very, very classical. They are called undrained because the volume is maintained constant. And now, if we plot the deviatoric stress as a function of the mean pressure, we obtain this kind of very classical experimental result. Here, the black line is the Moore-Coulomb line, and here, this is the experimental points with a peak for the deviatoric stress. These tests here are axially strain controlled. But if you perform now the same test, axially stress controlled or axially force control, of course, you will have a sudden failure at the maximum of Q peak. But at Q peak here, the determinant of M is strictly positive. The determinant of M is vanishing on the plastic limit condition. So classical plasticity cannot describe this kind of failure. So we can consider what is called the second order work criterion, which is the scalar product of d sigma by d epsilon. In axisymmetric condition, in principal axis, this second order work is taking this very simple expression here. And if we take into account the isochoric condition, constant volume, the second order work is just equal to dq d epsilon 1, where Q is the deviatoric stress. So this, the vanishing of this second order work can describe the peak of Q, and we will see immediately that this instability condition, the vanishing of second order work, can describe this Q peak, this deviatoric stress peak, which is not described by the classical plasticity. And now, if I write the elastoplastic relation like that for axisymmetric condition, that's possible for any kind of elastoplastic relation. You see that for an isochoric condition, d epsilon v is equal to 0, and at Q peak, dq is equal to 0. So you have a bifurcation criterion here, the vanishing of the determinant of this matrix N, and which is generalizing the plastic criterion, and a failure rule, which is generalizing the notion of flow rule. So just a few words about this second order work criterion, equal to the scalar product of d sigma by d epsilon. According to Hill, this is a sufficient condition of stability if this scalar product is strictly positive for any d sigma and d epsilon linked by the constitutive relation. And now, if I introduce the elastoplastic relation in this expression, I obtain a quadratic form with respect to the elastoplastic matrix M, and according to linear algebra, a quadratic form depends only on the symmetric part of the elastoplastic matrix. So the second order work can vanish when the determinant of MS is vanishing or taking negative values for the singular domain of MS. And I don't want to enter in technical details, but just have in mind that for associate elastoplasticity, like for metal plasticity, generally speaking, the elastoplastic tensor is symmetric. So the plastic limit condition and the stability condition coincide exactly for classical elastoplasticity, for associate elastoplasticity, like for metal. Now, if you consider granular elastoplasticity, which is strongly non-associate, roughly speaking, it means that the friction angle is strongly different from the dilatancy angle. But I don't want to enter in this kind of details. So for granular elastoplasticity, M is not symmetric. So both the classical plastic limit condition and the stability condition are different. And according to linear algebra, the determinant of the symmetric part of M is vanishing before the determinant of M and before the localization criterion. I will not discuss that. So you see that we have a bifurcation domain between the singularities of MS and the singularities of M. Since here, new developments have been proposed in the last years. First, it has been shown by François Nicot that the vanishing of second-order work is linked to bursts of kinetic energy, as we see in on failures of granular materials in the lab, but also in situ. We observe always this burst of kinetic energy, and we have now a general proof of the link between second-order work criterion and divergence instabilities, which has been proposed by Jean Lerbet using variational method. So we have here briefly the conclusion from a theoretical point of view. For non-associated materials like granular materials, we have a bifurcation domain, and in the vanishing domain of this quadratic form, according to linear algebra, we have cones associated with the vanishing or the negative value of the second order work and for us it means some unstable direction. So let us now check these results with elastoplastic relation. This is the simplest case, the case of axisymmetric condition, and in order to check various direction of the various incremental loading direction in the strain space or in the stress space, I will consider this class of proportional strain paths associated with various value of R. According to the second order work, the new expression for this class of paths of second order work is given here. We can write now any kind of elastoplastic constitutive relation like that, and at sigma 1 minus sigma 3 on R peak, we have this kind of condition. So the bifurcation criterion is given here, and in this simple axisymmetric case, when the discriminant of this equation of second degree with respect to the direction, when the discriminant is positive, it means when the determinant of the symmetric part of M is negative, we have two values for R. It means a cone of unstable direction. Here you have the results according to two different elastoplastic constitutive relation. The red line, we are in the axisymmetric stress space. The red line are the plastic limit condition of Morcoulon for granular material. And here in blue, this is the hydrostatic line. And the first point here, the crosses here, correspond to the first point where the determinant of the symmetric part of M is vanishing for this constitutive relation. So we have a large bifurcation domain between this red line in compression and this point. This whole domain here is a bifurcation domain in compression, and in extension, this domain here. Here you have the cones of unstable direction, and you see that for this elastoplastic model, we have a second cone of unstable stress direction, which is emerging close to the plastic limit condition of Morcoulon. This is indeed possible from a theoretical point of view. Now you have here a 3D generalization with here the limit of the bifurcation domain for one elastoplastic model and the limit for the other elastoplastic constitutive model. It happens that from a qualitative point of view, any kind of non-associated elastoplastic constitutive relation with hardening variable, any kind of these elastoplastic relation are giving qualitatively the same bifurcation domain. Here, this is the trace of this bifurcation domain in the deviatoric stress space. And here you have the cones of unstable stress direction close to the plastic limit condition. We see, because we have an incrementally nonlinear elastoplastic constitutive relation. I will not discuss this technical point. We have several cones, what means that the landscape of bifurcation, of instabilities, of failure, close to the plastic limit condition, generally speaking, in the bifurcation domain, is quite complex. Finally, we have here the three necessary and sufficient conditions for an effective bifurcation, an effective failure. First, the loss of definite positiveness of M, which correspond to the existence of a bifurcation domain. The determinant of MS should take negative value. Inside this bifurcation domain, when for the direction for which the second order work is taking negative value, we have cone of unstable direction. So to have an effective bifurcation, we need to apply incremental loading in this unstable, in this cone of instability. And we have also to consider proper mixed loading parameters. So when these conditions are fulfilled, and this is the case in many practical situations in situ, once more for earthquake, for landslides, and so on, we will have this kind of bifurcation leading to catastrophic failure not described by the plastic limit condition. The important point is, of course, that the classical plastic limit condition cannot describe all the bifurcation, all the instabilities, all the failures for granular material. So we have seen some experimental results at the beginning. We have seen some brief theoretical development introducing the second order work criterion. We have obtained some results by applying this criterion to some elastoplastic constitutive relation, but we have not seen an effective failure. We have just seen that we have a bifurcation domain, we have cones of instabilities, but now we have to check if we have effectively failure inside these cones. For that, we need to use direct numerical simulation, what is called DNS, and for granular material, the most known direct numerical simulation correspond to discrete element method. So with this discrete element method, we will check the existence of this bifurcation domain, the instability code, the question of the loading parameter, and because we have some bifurcation, this bifurcation will depend on perturbation, and we will see also that. So here, just a brief presentation of the discrete element model, which is constituted by 10,000 spherical particles in a cubical sample. The interaction law between the grains is extremely simple. An elastic stiffness in the normal direction, a tangential elastic stiffness in the normal direction, and a tangential elastic stiffness in the tangential direction with a friction angle, the very known Coulombian dry friction, limiting the tangential force by this friction. So the first question was, is it possible to obtain these cones with this discrete element method, which is, of course, a method fully different from phenomenological elastoplasticity. So you have here a polar diagram of the second order work, where you have in each incremental stress direction the values of second order work. This circle here, this internal circle here, correspond to vanishing value of the second order work. So inside this circle, for this point, it means for this direction here, we have negative value of second order work. So you see that according to DM, we have this cone of loading direction corresponding to negative value of second order work. Of course, at the beginning of the loading, the second order work, close to the hydrostatic axis, the second order work is not taking negative values. We have to enter inside the bifurcation domain and to obtain this cone of unstable stress direction. Okay, now we have this cone, but is it possible to obtain a failure inside these cones? So we consider all these direction, all these values of R corresponding to direction, to incremental loading direction in this stress space. We have here the cone of unstable direction. And of course now, some direction are outside of the cone, some direction are inside the cone, and here both these directions are just at the border of the cone. So which are the result with discrete element method, which are the result in relation with a proper bifurcation leading to an effective failure. The results are here. So for this direction, blue, and this red direction here, outside of the cone, nothing happens. The stresses are perfectly stable. The strains are perfectly stable. Inside the cone, black and red, the stress are no more controllable, and the strains are growing exponentially. So we have a proper failure inside the instability cone. And just at the border of the cone, for the purple line and the green line, we have this kind of erratic behavior just at the border of the cone. Very interesting. Okay, here this is for the same condition, the exponentially grieving strain, nothing, not any variation outside of the cone, and these erratic, chaotic variation at the border of the cone. Now the question of the control loading parameters. For that, we have considered one particular direction inside the cone, a constant deviatoric stress for axisymmetric condition. This kind of loading direction is interesting because in practice, for landslides or for earth dams, this is a loading direction which has been effectively observed in practice in the slopes or inside earth dam. So we will consider different loading parameters. First, a loading path which is fully stress controlled according to the theory. For these stress control paths, the stability is maintained, and still according to the theory, to the second order work theory, if we have this mixed loading, control on the deviatoric stress, which is maintained constant, and control on volume variation, applying negative value. Indeed, we have an effective bifurcation, an effective failure for the mixed controlled, here, non-controllable stresses. Nothing happens for a stress control. Here you have this burst of kinetic energy for the mixed control and just a small variation for a stress control. Here you have the strains, exponentially growing strain for the mixed control. And finally, the question of perturbation. We consider this state by imposing these loading condition, which can be stable outside of the cone, unstable inside the cone, and so on. And we apply a small perturbation to the specimen by giving some velocities to the floating grains. The simulation by DEM are performed without gravity. So among the 10,000 spheres, we have always some very few floating grains. Here you have the results for this perturbation. Outside of the cone, more or less, nothing happened, just a small variation of the kinetic energy. Inside the cone, a sudden burst of kinetic energy and non-controllable stresses. And at the boundary of the cone, this chaotic variation. Okay, so the second order work criterion has now been properly validated by a discrete element method, by direct numerical simulations. So indeed, we have proper failure, proper bifurcation inside this instability cone, inside this bifurcation domain. Now I will finish this talk by considering the example of an Italian slope failure, a very known landslide in Italy. You see that this is a landslide with a large failure, large displacement. This site is along the Adriatic coast. This is a very large landslide, 2 kilometers here, more or less 1 kilometer here, and this is a dramatic landslide because you have some villages, some roads, a motorway, and so on. So this landslide has been extremely well studied, and a large European research program has been devoted to analyze this landslide. And this landslide was considered as fully unexplained by a classic Moore-Coulomb criterion, because you see that the slope of this landslide is extremely low, 6 degrees. It is not possible, of course, to explain such a landslide with a Moore-Coulomb, with a classical plasticity criterion, the Coulombian criterion, for which a slope is unstable, let's say for 25 or 30 degrees. So in the framework of this European program, we have applied in a finite element model. You have here at the bottom the mesh of the finite element model. We have applied our second order work criterion. Here you have the loading program. First, the soil is dry. Then we have increased the water table level because in practice this landslide was effective after strong rainfalls. So, of course, the water is responsible for the instability. And we have calculate in each point of the mesh, in each material point of the mesh, the local value of the second order work, and also we have considered the global value of second order work. I have not discussed this second point, but the integration of the second order work is linked to a global instability factor. Okay, here you have the result. In blue, this is the increasing water table level. And you see that when the slope is fully saturated, it means when the water table level is reaching the free surface, according to the local value of the second order work, this part of the slope is potentially unstable. Once more, with the classical plasticity analysis, this slope was considered as perfectly stable in contradiction with the observation. Okay, here this is the global value of second order work. The effective bifurcation, the effective instability, the effective failure correspond to the vanishing of the global second order work. Here you see we are very close to describe the effective failure, and indeed at this point the finite element computation was no more converging, so we have not been able to continue the loading. But you see that the global second order work is a very good indicator of failure. Okay, that will be my last slide with some conclusion. First, granular media are perfect complex system with some specificities, and an important feature is this non-associated plasticity, leading to non-symmetric matrices, constitutive matrices, and this non-symmetry is, as we know, generally speaking in physics, this non-symmetry is leading to various bifurcation. We have first observed these bifurcation on experiments. We have a theoretical proof by variational methods. We have see what kind of results have been can be obtained by elastoplastic phenomenological relation, and validate also all that by direct numerical simulation. And if you want to have more details about all that, the first book here is considering granular material with non-associated plastic behavior, but the same kind of reasoning have been developed for non-conservative elasticity. And we know that for non-conservative elasticity, the elastic tensor is no more symmetric. The same reasoning can explain with the second order work criterion can explain the paradoxical instability which have been observed for some non-conservative elastic structures. So thank you for your attention.